Consider now the definition of the flux. Assume that we have azimuthal symmetry, so this is 2 pi integral I cosine theta sine theta d theta. Now do the substitution mu for cosine theta, so that the flux is 2 pi times the integral of I mu du nu. So if this is a closed integral and you are integrating from 0 to pi, the integral mu is going to be from -1 to 1. Now substitute the intensity given by the Rossland approximation. Now the flux here is, now I have mu square here because mu is cosine theta. So the first term here, if the Planckian is isotropic, this is going to cancel. Remember, you are in the center of an isotropic field. The second term is the deviation from the isotropy. That's what's going to leave you a residual flux. Now this integral here is simply 2/3. So the flux is minus 4 pi over 3 over kappa rho times the derivative of the Planckian in z. Now, since the Planckian does not depend on the depth, but it depends on the temperature, then you can use the chain rule to replace it by a temperature gradient. The derivative of the Planckian in z is equal to the derivative of the Planckian in temperature times the variation of the temperature in z. So you can already see where the temperature gradient comes from in the definition of the flux. So this is the monochromatic flux. You can integrate in frequency to find the bolometric flux. And the only quantities here that depend on the frequency are the opacity and the Planckian. So now to bypass the frequency integration, you can define the Rossland mean opacity, which is a gray opacity. You see here, you have in this integral 1 over the opacity times the derivative of the Planckian in temperature. So the Rossland mean opacity is defined as Kr, let's call it kappa r. You have that the Rossland mean opacity is a weighted mean. So even though the numerator in the Rossland mean opacity is not known because of the dependency of the opacity on frequency, the denominator can be evaluated. The integral of the derivative of the Planckian in temperature is equal to the derivative in temperature of the integral of the Planckian, since the operator is linear. And you know that the integral of the Planckian is 1 over pi times sigma t to the 4th power, which is then 4 sigma over pi times t cubed. So I have an expression for the integral then in terms of this Rossland mean opacity that we just defined. If the denominator is 4 sigma over pi times t cubed, then the integral is 4 sigma t cubed over pi over the Rossland mean opacity. So you can substitute this integral into the flux. So then finally you have the flux. So this defines the temperature gradient that carries the flux if it is carried by radiation. The Rossland approximation is a very good approximation for the optically thick case when the optical depth is much, much bigger than 1.